So how many people did this background survey? Anybody not done it who wants a minute to do it? If you haven't done it, I'm going to give you like 40 seconds to do it right now. Okay, so I'll just pause for a second, and I'm going to, yeah, go fill it out right now if you haven't filled it out. It's the link is on Quarkus. It will not take you very long to fill out. I have another question. Can you hear me in the back? I was here last night. I actually checked the wireless mic was here. It was here. Someone stole it today. So if it was one of you, bring it back. I don't think it was one of you. I think it's one of the previous lecturers was probably having so much fun that he or she just took the microphone with them. But yeah, let me know if you can't hear me very well, and I will speak louder or turn on this thing. Don't worry, we're still doing logistics here. I just found it here, so if it took a while to find, you're right on target. So I'm going to go show the background here. And let's see, I'll refresh this. Okay, so just need a moment to fill this in. If you're filling it in, press submit right away, or you're not going to show up in the results. You'll be sad. All right, so I'm going to take that as you've filled it out. Oh, that's the wrong thing. I want to go to view responses. So yeah, it's been interesting to see what the class looks like. So you guys might be interested in this too. So about, whoops. So we're about 1/3 research stream students, so PhD and MASC, and the other 2/3 approximately is MEng, with about half people being full-time MEng and a good chunk, 20% being working. So that's interesting. So see what the class is about. Okay, so for those the 16 people who are here part-time while working, where are they? AMD is the number one, but lots of different ones. So Altera, AMD, Evertz, which is a video processing company that I used to visit back when I worked at Altera, out in, I think it's in Burlington. So click on the more details. Yeah, you can see where everybody's working. So a bunch of different companies. That's great. I mean, I like actually participation. So people who are working, often you have interesting perspectives of, hey, that doesn't actually really work. We tried that. So let me know. What's your primary research area? So here's kind of the scatter plot of that. So digital design, computer architecture, FPGA architecture, acceleration, so learning acceleration, reconfigurable architecture, CAD tools. So lots of different things. I've looked at these offline, so I was looking at them already. There's actually a lot of people whose research area is in FPGA, CAD, and architecture. And then a bunch of people who are in digital design of various types and electronics of various types. Some deep learning acceleration, which is a pretty hot topic these days, and high performance computing. So pretty diverse group of people. It's a lot about FPGA architecture here, so I was really happy to see a bunch of people who that's a research area. What hardware description languages have you used? So Verilog and System Verilog, which are really System Verilog is really just the next generation Verilog. I don't entirely understand why they call it the System Verilog. I guess it's kind of branding to some extent. It's really just the next generation. In North America, Verilog and System Verilog are more popular. But VHDL, a fair number of people know too. In Europe, VHDL is more popular. And then a few people either know other HDLs or don't know it. I mean, this course is not primarily about HDL design, but the first two assignments use HDL design. So that's why I ask. If you don't know HDL, you can learn it. You'll just have some more background to pick up as you get to that. There's some pretty strong links between trying to make a good FPGA architecture and making computer-aided design tools to investigate, what's good and bad. At the scale of circuits that you're putting in these devices, you can't do things by hand, so you need automation. So Professor Anderson's CAD for digital circuit synthesis and isn't required for this course by any means, but it's pretty complementary. So that's why I asked how many people are taking it, and about a third are taking it, so I won't assume any background knowledge there. But again, a very complementary course if you're really interested in this area. We'll be doing, because we're talking about programmable logic, we'll be talking sometimes about digital design at the gate level. And it looks like most, but not all people are familiar with that. And then you're trying to figure out what's efficient to put in an FPGA architecture. You sometimes have to go below the gate level. You have to think about what transistors am I really building. And it looks like about half of people know how to do transistor level design, and about half people don't. Level design, the part that's relevant to evaluating an FPGA architecture in this course. I don't really assume a lot of background there. So you'll pick up some, and you don't have to go super deep. What are you hoping to learn from this course? So this is good, right? You never quite know, like, did people just sign up by accident? But they didn't, right? So the number one thing was FPGAs, reconfigurable architectures, design on FPGAs, architecture of an FPGA, Verilog on FPGAs, FPGA basics. So that all looks good. If I take a look at more details just to see, this is actually very helpful, right? So it's pretty on point for the number one thing. People want to know more about what's inside an FPGA. So not just how do I use it, but how do I make a good one, what's inside it, which is a focus of this course. Some about how can I get more out of an FPGA, how to write better HDL course. You'll get some experience in that in the first couple of assignments, and you'll know what's going on inside of it. All those courses not primarily about, just optimizing digital designs. It'll have that, some of that, but that's not the number one focus. Yeah, so all these, and then this was interesting. So 3D stacked and heterogeneous FPGA designs. So FPGAs for accelerating, very detailed. And actually, these are a lot of hot topics, so we'll talk some about this, right? So one of the things that's happening in computer architecture in general is that we're building systems out of more than one die. We'll talk some about that in the FPGA context, and then I'll give you also some general knowledge if you don't know about 3D stacking techniques and how those work. We'll also talk some about accelerating computations with FPGAs, and one of the big computations people like to accelerate these days is AI. So that'll be some of the papers and some of the discussions we have. And yeah, so that's pretty on topic. Okay, and then the last question. If you were a tree, what kind of tree would you be? You can see the problem with the word cloud. It basically said the number one response is tree, which is not highly informative for me. But you see, like, lots of different things. There's a few people who are really heavily into computer engineering, so they'd be a binary tree. They're completely now divorced from the natural world. They haven't been outside in years. Their advisors probably love them, but it might be good to go in the park sometime. A lot of different ones here. I had to look up, so teak tree, cedar tree, oak tree, pine tree, palm tree, magnolia, beautiful tree on our street. I had to look this one up. Osmanthus tree, so it's a flowering tree about 5 to 7 meters tall. Looks very pretty, so I learned something new. Here's another engineer, search tree. So you can see all of, and actually it didn't pick them up, but another couple I liked are redwood and sequoia, which are closely related actually. Those are both redwood. And yeah, so here you can quickly see some of these responses. So let's see. So I won't go through all this. Oak is pretty popular, lots of diversity here. Okay, so why did I talk about your favorite tree? Because I actually really like trees, okay? Which is, so I just put it in here. Doesn't really fit in the course. I don't really care, okay? So my favorite tree, I like actually all those trees. I was out hiking one time years ago with my wife in Algonquin Park, and there was this really big white pine. I wanted to see how big it was, so I put my arms around it, try to figure out the circumference. She goes, Vaughn, you were like literally hugging a tree, right? Like, so I like trees. This is a giant sequoia, so a variation of redwood. It's in the mountains of California. They actually name these trees. They're so huge and so old. So this one's called General Sherman. It's 3,000 years old. It's 275 feet tall, so it's like about 90 meters. 37 feet diameter, weighs 4.2 million pounds, so like 2 million kilos. It's the world's largest tree, so it's pretty cool. It's actually not the tallest tree. That's another variation of redwoods. The coast redwoods are not quite as wide. They're on the coast of California and Oregon. The tallest one is 370 feet tall, which is like 115 or so meters. So like the height of, a 35-story building or so. So for a lot of like cities, this would be taller than any of their buildings. So if you go to California, these are cool to visit. This is actually just north of San Francisco. So these ones are easy to go to. These ones are about 3 hours west of San Francisco. And yeah, they won't actually tell people exactly where this tree is for the reason that there'll be some stupid person who might harm it. But basically, there's somewhere in Northern California a redwood that is the tallest in the world that's 370 feet tall. Okay, so enough about trees. Overview of the course. So I posted a syllabus on Quarkus, so you can go there and get more detail. We're going to talk about, I guess, kind of broadly three things, like lots of things within that. But first, how to use FPGAs. So the first part of the course is a bit about what's in an FPGA, but then let's try to use these things. So why do they exist? What are they good for? What are they not so good for? So we'll talk some about that. FPGAs are like a blank sheet of paper, right? They're programmable logics. You can put anything in them. So it's useful to think about what are different ways you can organize a computation, which are called programming models. And that's not specific to FPGAs. It's actually useful in general. If you're trying to make hardware accelerators or high-performance computers, what are different ways you can organize the computation? But it's particularly useful in an FPGA context because you've got this kind of piece of silicon that you can program in any way you want. So you need to sort of think about how am I going to organize my computation. What are their strengths and their weaknesses versus other devices? So when would you want to consider them, and when would it be better to go to some other device? And then some key applications and how we actually can get good performance on FPGAs for those applications. So two of the really interesting ones these days are accelerating deep learning applications. So a lot of matrix math and repetitive computations, and data center infrastructure. So a lot of computation in data centers is moving into what are called smart NICs. So network interface cards that can actually process data on the fly without it kind of loading up the CPU and adding latency and power. And FPGAs have been pretty successful there too. Okay, so that's kind of the first few lectures are on that. Then we move to how do we architect FPGAs. So we take a deeper look inside of them. How do we create the function blocks, so the logic blocks, the RAM blocks, the DSP blocks that go into them? How do we make the programmable interconnect that lets us wire all that stuff together in different ways, efficient? Clocking is difficult when you have to do it programmably. So what do we have some techniques for that? And more integration, which means more than one piece of silicon. So we can use chiplets and something called chiplets and interposers and combine them. We can also stack things in 3D. Now you can do that for all sorts of different technologies, but interposers have been heavily used with FPGAs, and there's research going on into the 3D systems as well. And in general, I'd say this is a pretty interesting technology that's not FPGA specific, so it's nice to learn about because it is also a good match to FPGAs, where you're kind of trying to make big programmable systems, so having more silicon tightly integrated is good for them. And then some coverage of alternative spatial devices. So we're not going to talk only about FPGAs, though we'll talk primarily about them. So there are other variations on what are called spatial architectures. So spatial architecture basically means I've spread my memory out over my silicon die. So FPGAs are the most successful and probably best example of that. But another kind of device is called a coarse-grained reconfigurable array. It's a lot like an FPGA, but it tends to use sort of blocks that are a bit bigger and route entire buses of data programmably. So closely related to FPGAs, we'll talk a bit about them, and a commercial example, Samba Nova, which is a machine learning acceleration company. Their chip is a coarse-grained reconfigurable array. And spatial processor arrays. So why do I put this in the same category? So a spatial processor array is you make not one core, not two cores, but like a very large number of cores. So I actually work part-time at Cerebras. Cerebras has nobody hears from Cerebras, right? So it's not because I'm going to say something bad about Cerebras. It's just that I start asking questions about Cerebras, and somebody in the audience works at Cerebras, then I expect better answers from you. Okay, so who here knows what Cerebras is? You ever heard of them? Okay, so a few people. So I'll give you a hint. Cerebras, they make machine learning acceleration silicon, and their claim to fame is that they don't cut the wafers, which are about 12 inches across, or 30 centimeters in metric. They don't cut them into a whole bunch of chips. Instead of cutting that into like 35 big chips, they leave it as one giant chip. That takes a whole bunch of special technology. It's the only wafer scale integration that I know of that's been successful. So got a giant, try to borrow actually one of these and bring it in here. They actually sell for like more than $1 million, so I have to be very careful with it. Probably won't give me one that works, but even one that's a prop, they probably really don't want broken. Okay, so they basically build processors in a 2D array connected by programmable interconnect, okay? And so that's a spatial architecture because you have a lot of processing that is spread out in two-dimensional space It's connected with programmable routing, and you need to know where your data is. In an FPGA, you know where your data is where you put it, right? You don't just ask for some address and it magically comes back from a memory. For most of your data, you've been thinking about where am I putting it on the chip, or the CAD tools have been helping you decide where to put on the chip. So that's why Cerebrus is in this, I would place them in this broad class of programmable spatial architectures, even though their computation is actually done by processors, not by these logic blocks and RAM blocks, but they have aspects of the spatial architecture. So how many processors do you think they have in their system? There's no particular reason you would know this, right? So it's kind of just a random question, but it hopefully wakes you up. So anybody want to take a shot at this? 1,000 processors? Not bad, okay? So anybody else? We're going to have a few guesses. We're going to see who's closest. So remember, 1,000. Any other guesses? 4,096. Any other guesses? That's it. 300,000. 300,000. What do you think? 999. Wait a sec. So one lower than 1,000. Okay, so you watched The Price is Right. Because you can't go over. No, wait, you should go $1. You should go 1. But it's just closest, okay. They have just under 1 million, okay. Depends on the generation, because they're actually making the processors a little more powerful generation by generation. But it's about 1 million, if you were to round it off. So, you know, that gives you actually a big spatial problem. You have 1 million processing cores, and they each have their own data and have to exchange it through this programmable interconnect. That has a bunch of similarities with FPGAs, where you have millions of lookup tables and tens of thousands of multipliers and stuff communicating through this programmable interconnect. Okay, so we'll talk some about these alternative architectures too. Okay, so I know nobody probably cares about this, right? You're like, I don't care how you're going to evaluate me. Just give me a random grade. It's all about the learning, right? And I understand, but I'm still going to tell you how you're evaluated. So before assignments, that's the bulk of your grade. The first two are on hardware description language design optimization on current FPGAs. So generally, you write this in Verilog. We give you test benches in Verilog so you can check if it works. You could write in VHDL, but it's just a little more plumbing to connect them together. So what you're going to do is we're going to give you, the first assignment is going to come out soon, like in a week or so. And it's not that complicated. It's basically largely a tutorial on the CAD tools and how do you analyze a design and so on, and how do you simulate to make sure it's correct, et cetera. And what you're going to do is we're going to be studying programming models, like different ways to organize computations. So you're going to do the same basic computation a few different ways to see how efficient it is, okay? And part of the value add here is actually just learning how the tools work and how you go through this procedure. The second assignment is similar, but you're going to do a bit more complicated HDL design. You'll do convolution, so image processing. It's also an important part of a lot of neural networks. And you'll try to make it fast. So you're going to basically try to optimize that. We're also going to give you the code to run on a GPU so you can compare it to a GPU and see how efficient they are. Then we kind of switch gears. The third assignment is we're looking at inside of an FPGA, how we make a decision on what's a good versus bad architecture. The specific question we're going to be looking at is how should we design the RAM blocks inside of an FPGA? And to look at that question, you need automation. You need something that can automatically take a bunch of designs and say, I would implement it this way and it would work this well. So this one, you're going to be writing software, algorithmic software. So you'll write a form of CAD tool, which is called a RAM mapper. And this is inside if you use Vivado or Cordis, they have this technology, something like this, right? They obviously don't have your code, but they have some technology like this inside their CAD flow that takes the RAMs you've asked for and figures out how to put them on the chip. So you're going to write a tool that does that. You're going to try to make it do a good job, because this actually is an optimization problem where you can't find a perfect solution, usually, in a reasonable CPU time. And then you're going to use that CAD tool to sort of change the architecture of the FPGA. You're going to say, well, what if I did this in the chip? What if I did that in the chip? And see how that affects the efficiency. So you're answering a question that an FPGA architect would answer. You can write this in any programming language you want. So lots of people write it in C++, some write it in Java, some write it in Python. Doesn't matter, right? You just need it to work. We give you a verifier so you can check that your solutions are legal. And you need to pick an algorithm. You'll probably wind up tuning it over time and trying a few things. And yeah, write it any way you want. And then the last assignment is use any existing larger CAD tool. So a CAD tool called Verilog routing, or VTR. It's an open source CAD system that can target a wide variety of FPGAs. So you can change the FPGA it's targeting. You're going to take it and you're going to use it to try a few different things in terms of how the programmable interconnect works and see what works well. It's a large tool, so it's hundreds of thousands of lines of code, but you don't have to change it. You're just going to run it. You're going to learn how you can control it and how you can use it to answer some architecture questions. OK, so that's kind of 4 assignments. Any questions on any of those? And don't worry, this is kind of an overview. You're obviously going to get a detailed description of this during the semester. Yeah?
Those of us that are more familiar with VHDL rather than Verilog, are you going to provide us with a little overview of Verilog?
Yeah, well, I'll point you to resources. And then we have a PI discussion board so you can ask questions about it. You don't need to be very expert. Like, you can learn what you need in Verilog quite quickly. So I actually am better at VHDL than Verilog actually as well, because it's the language I learned better. But I can just kind of map the concepts to Verilog. You can write it in VHDL if you want to. It's just we wrote the test benches in System Verilog, so hooking those together is a little bit more of a pain. You may find it just easier. I suspect it's actually going to be easier just to go, I'll just write it in System Verilog. You're not writing huge amounts of System Verilog or using very complex constructs. Does that make sense? OK, so you're also going to read some papers. So most weeks I'll assign 1 or 2 papers to read, and there's a short questionnaire. They'll ask a few questions just so you can verify your understanding and show us that you read the paper and understood it. They're not very long. They ask a few questions. It might be a page of writing, might be a bit less. They're worth 1% each. So you want to read and submit at least 10 of these questionnaires to have a shot at 10%. But if you do more, it'd be great if you read all of these, right? Then you're learning more from the course. If you do more, then we'll take your best 10, right? So we'll drop whatever the lowest ones are. And at the end of the course, if I've got somebody who's read all 20 and done a good job on them, I also usually kind of will give them a little bit of a bonus for that. I don't have an exact formula for that, but I kind of go, well, this person kind of exceeded on that. So you want to read and submit at least 10 of these. You could do up to about 20 if you read every single paper and submitted a questionnaire on them. But this gives you some flexibility if you're really busy some certain week or some topic resonates with you a lot more than another one. OK, and then we're going to have a couple of in-class quizzes/tests. So they're worth 25%. There'll be one. So I haven't done this before, but I'm going to do it this year. So we'll announce them in advance. I expect I'll have one that's worth 10% probably halfway through the course, and one at the very end of the course that's worth 15%. I don't plan on making these terribly difficult, so I'm going to get feedback from you of how this went versus what I've often done in the past is people write a research survey paper, but as the class has kind of gone more towards MEng, I think quizzes might actually suit the class better. There's also a problem of, as the class keeps getting bigger, it's actually difficult for me to mark 60 or 70 research survey papers. But this will actually be useful feedback at the end of the course. You can tell me if the tests were a huge source of stress. My plan is for these not to be extremely difficult. The idea is if you've come to lecture, you've watched the slides, you've done at least most of the reading, that you're going to do fine. OK? So it's not intended to trip you up. It's just to check, have you been keeping up with the course material? Yeah?
Is there a specific format for these? Or?
You're going to come into this lecture. We're going to give you a piece of paper. And we're going to make sure that it's not too hard for you to write nor too hard for us to mark.
I guess I was wondering if it was closed book or open book.
It's going to be closed book, because if it's open book, then it kind of starts getting. So my plan is to make it closed book, because I think otherwise it just gets too hard to kind of administer, right? Because you probably don't have everything printed out, so you're going to wind up with a lot of computers, and it's going to be hard to figure it all out. But my plan is not to ask extremely tricky questions where. Oh, I didn't memorize that. If you come to lecture and then you kind of review the slides before the test, you should be fine. Does that make sense? And you come to lecture and you actually try to pay attention, OK? So I'm not saying if you're physically here, but you're on your phone the whole time, that might not actually be good enough. So, and like I said, actually, you can give me feedback during the course or at the end. I am curious, because this is a change from how I've done the course in the past, where people had to write instead a 6-page research survey paper. Actually, I guess I'll ask you right now, how many people think that sounds better? Because it is less work, right? It's less work than at the end of the course writing a long paper. So how many people like this idea, or how many people like picking a topic and writing a research survey paper? You'd rather do, okay, so how many people would rather do a paper? Okay, how many people would rather do quizzes? Okay, so actually more people would rather do quizzes than papers. So that's actually, I've been agonizing about this. So Sahel, I'll introduce Sahel. Sahel is the TA for this course. He's been listening to me agonize about this, going back and forth. So you can, this is somewhat comforting. So, okay, so all the assignments are individual. Okay, and I mention this because it hasn't happened often, but it has happened occasionally that we've had students who've collaborated too much, and then there's an academic integrity violation. So I don't want that to happen to anybody. So the assignments are individual. It's fine to discuss with each other, right? That's part of learning in grad school. So general discussion of like, hey, what do you think of this? What do you think of that? Why do you think this bug is happening? That's fine. If you're in doubt, if you go, this is getting pretty detailed, then ask me. You can also post on Piazza, so you can always ask in the open, and other students can answer, and Hale or I can answer. So you don't want to do a joint solution or summary. If you're sitting there, you're basically writing something together, or you're both looking at the same screen, okay, that's where it usually gets too similar. So don't do that. Everything that gets submitted on Quarkus always gets sent through a plagiarism checker. So it generally flags it if it's really close, so just don't do that. When you're doing these paper summaries, it also means you shouldn't copy text verbatim from the paper. Like if we ask you a question, summarize this, do it in your own words. And that's just general research practice, right? You should never be, unless you put it in quotes. If you put it in quotes and cite it, then you can do that. But otherwise, you shouldn't be copying text verbatim from a paper. Okay, so if you want help, post on Piazza. Public posts are usually best, because if you have a question, then probably also other students do too, and maybe a student can also help you. So in general, do a public post if you can. But if it reveals a solution, like you want to post a bunch of your code, okay, that would be good to make private. If you're just really shy and you want to post it privately, that's okay too. But in general, if you're going, I wonder if I should make this private, I don't really care, well then probably make it public. I haven't made any defined office hours. Just contact me if you want to talk about something. If there's a lot of demand, I could make some hours probably on a Friday, but if there's not that much demand for office hours, I'll just do it by email. Okay, so we're going to try to record the lectures, and we're actually live streaming them too, so that it's actually better to come here in person. So I'm telling you that with a little bit of trepidation, because I don't want you to go, oh, I can just stay in my basement all semester. It's not a good approach. And we're also not guaranteeing we won't have technical glitches, because Sahel is a gifted graduate student, but he is not a professional videographer. So we're going to see how this goes. We start at 10 after all the time, like U of T time. So for those of you who are out working, yes, 5 o'clock at U of T does not really mean 5 o'clock. I worked many years at Altera. I guess I should actually tell a bit about my background. And I never lost the habit I got from my PhD, which was here, of being 10 minutes after the hour for everything, including presentations to the chief operating officer. I don't know why I did this. I was in San Jose. I was pitching like power-driven CAD tools and power-driven architecture. I wanted $5 million to start a new team and stuff. And just inexplicably, I showed up 10 minutes late. The CEO liked me, so he didn't complain about it. But as I was like getting really stressed, going, wait a second, I got to get there, I couldn't explain it. But trust me, we will start at 5:10. I'm never going to make it here for 5. I'll post the slides and scans of any handwritten notes. So we'll do some things on the chalkboard, and I'll post scans of that too. And yeah, it's good to have interaction. So if you've got questions, you've got a comment, put up your hand. Appreciate it. There's no direct participation marks because it's just too hard to keep track of, as the class is somewhat large, and I'm terrible at keeping track of people's names. But I get to know usually the students who participate a lot, and I will consider that in your final mark as like kind of a tiebreaker, right? Oh, you gave me lots of good questions, like give you a bit of a boost. So there's some payoff. Okay, so now I'm going to switch. So actually, I'm going to switch over to any questions on the course structure. Okay, sounds good. I guess I've forgotten also to introduce myself. So I've probably introduced like, who am I? What do I do? So obviously I'm a professor here. I haven't always been a professor. So I did my PhD at University of Toronto, and I developed basically a new way to look at FPGA architecture. You're going to see some of that in this course, using parameterized CAD tools where you could change the architecture, target a bunch of designs at the proposed FPGA, and see what works well. And that tool got a lot of industrial interest. as I finished my PhD. So I created, with 3 other researchers here at U of T, we created a company to commercialize it called Right Track CAD. And our initial customers were Altera. We were basically taking a try at replacing their CAD tools with ours. They wanted to see for their existing chips, could we do a better job? And our other major customer was Cypress Semiconductor, which at the time made their own FPGAs as well. But for them, we were developing a new chip. So using those same CAD tools to say this is how you should change your chip. Things went well. Altera did actually replace the algorithms and the heart of their CAD tools with the algorithms that we came up with. And we told them these algorithms are actually better suited to different chips. We could make your chips way better too. So they don't tell you this in advance. We figured out later that their executives believed that argument, but they were like, there's no way we're going to have an external company developing our CAD tools and our chips and selling them to anybody who asks. We would have been happy with that, but they saw some business problems with that. So they made an acquisition offer that was good, and we became part of Altera and the Toronto Research Lab for Altera, which is still here, just off the edge of campus. So I ran that research lab and large parts of the development of Quartus and the first 5 generations of the Stratix FPGAs for Altera. So I did that until 2011. So I was in industry from 1998 to 2011. And I always wanted to teach one day. So in 2011, I left Altera to come here and become a professor. And I made this course. And now you will see if I made a good decision, right? In 13 weeks, you'll be able to say, you should have stayed at Altera, or I'm glad you made that course. My research here at U of T focuses on a lot of the things I'm talking about here. How do you make FPGAs better? How do you make computer-aided design tools that automate the translation of a design into that chip better? How do you accelerate certain important applications? So, for example, some machine learning applications we're accelerating on FPGAs, and some different architectures that have aspects of an FPGA but not entirely an FPGA. And for example, working with Cerebras, so that would be an example of quite a different architecture that still has spatial characteristics. So that's kind of an overview of how my research fits into this. And some of that, so you'll see kind of, I guess, my biases coming through in the lectures. And if you want participation marks, you can challenge them, right? You can say, wait, you're coming from an FPGA perspective. I challenge that. So yeah, go ahead.
I guess this is more of a question. So I know some professors who used to work on FPGAs and maybe pivoted away from it a little bit. I guess I'm wondering why you kind of stayed the course a little bit.
Well, this is a good question. I mean, profs, one of the nice things about being a prof is you just kind of can follow your own interests. So I like CAD tools and I like coming up with different architectures. So partly it's just you're interested in it. I guess a lot of my research in FPGA architecture, some has been in like kind of how do you make better programmable routing and better lookup tables and stuff. But some has been more system level features. You'll see this later, like how do you put networks on chip in them? How could you change the DSP blocks to be better for machine learning? So while that's still tied together by FPGAs, it's a bit different than traditional FPGAs. And the network on chip work, you'll see it later in this course. Myself and one of my PhD students we did that. And it's unclear if the industry is saying this looks like a really good idea, publishing papers on it. I can come closer to you. Oh, it's okay again? Okay, thanks. Okay, so we take T2 times T1. Okay, so that's AX plus B is in T2, and multiply it by T1, which is X. And now we're almost done. And then we're going to write, so we needed this B in a register file. And now we're going to store our final answer, Y, by getting T2 plus C. Okay, so we had to have C in here somewhere, and we put Y in there. Okay, so this whole thing is sequencing through, being decoded, controlling these control signals to say, well, what do we read out? What do we write back? What operation are we doing? Is it a multiply or an add, etc. So this is our instruction stream. So we usually call this a temporal calculation. So it's in time, right? We're building an answer up over many cycles by doing one thing at a time. Okay, so it's another way of saying it's sequential. So that's obviously one downside for speed. This took me a bunch of steps that I had to do one after another, so it just took longer. Is this register file a problem for going fast? It's kind of a hint. Maybe it is. What do you think? Yeah, so this register file can become a bottleneck. How fast can I write and read it? So in this simple processor I've made, I only have a few registers. But if I want to do a more complicated calculation, I need to make this register file bigger so I have enough temporaries. And it's very easy to program. I have all my data in one spot, and I just give like the address, and I get that data. But it becomes a bottleneck. It becomes a bottleneck because I'm putting all the data in one spot, getting all the data out of one spot. It's expensive to add more ports. Okay, so I've got 2 read ports, 1 write port here. It's actually quite expensive. As you make this thing bigger, it gets more power hungry, and adding more ports makes it worse. So if I'm trying, basically the thing that makes this easy to program, which is all my state is just in one spot, also is a fundamental bottleneck. If you have a lot of state, trying to get a lot of results out of it, trying to make a large storage becomes less efficient in power and less efficient in time. Okay, so we have this global or centralized state. Now this is a very basic processor. It does one thing at a time. So, and there are processors like this, right? If you want a really cheap microcontroller, this is exactly how it does it. If you want to go faster, a processor can extract a limited amount of parallelism by figuring out that some of these instructions don't depend on each other and essentially overlapping them. So processors can do better. They can extract some what's called instruction level parallelism. Okay, so ILP or instruction level parallelism. But it's limited. They can only find usually a limited number of independent operations by looking at these, and it takes a lot of hardware. It's actually a lot of work to have hardware figuring out that these two things could happen at once. In the example I gave you, there really isn't much instruction level parallelism because these are all depending on each other, but in some other programs there might be. Okay, so this needs lots of hardware to extract. The more instruction level parallelism you want to extract, the more hardware you need. You actually look at basically bigger and bigger windows of instructions, trying to figure out things that could be executed at the same time, and it takes quite a bit of power. Where I could get instruction level parallelism here is I showed one number. What if I was doing this in a loop, which is more likely? Okay, so I've got a whole bunch of x's coming in, I've got a loop, and I've got a whole bunch of y's going out. Okay, now I actually do have some instruction level parallelism because there's no dependency for the different, x1 and x2 and x3. Those produce y1 and y2 and y3. So now there is instruction level parallelism. A more complicated processor could overlap them, but it's going to pay a bunch of hardware to figure that out at runtime. Okay, so let's contrast this with hardware. Let's see if I can erase this. Okay, so I guess hardware is, I'm going to show you more optimized hardware, okay, like a spatial, more parallel hardware. I mean, a processor is hardware as well, okay, so everything's hardware. That's why we'll talk a bit about programming models. But what if we don't use this processor style of computation? We instead use something that's a little more hardware friendly or optimized for spatial hardware. Okay, so what I can do now is I can just build all the operators. So I can have this, I was doing this AX, well, I'm doing the same calculation, which unfortunately I erased, but basically I need to get AX squared, okay, so I can build a multiplier for that. And then I needed BX, so I'll build another multiplier for that. Then I needed to multiply by A. Okay, so I want AX squared, so I'll build another multiplier for that. I'm building an ALU to add in C. Okay, so I was supposed to take BX plus C. And I don't actually have to build a whole ALU here. I'm basically building a whole hardware unit that only does one thing. So I don't actually need to make an ALU that can add, subtract, multiply, whatever. I'll just make an adder. Okay? So I can specialize the hardware more because I have now kind of built a spatial compute unit that does just one thing. Okay, that goes down here, goes over here. Okay, I need another ALU or adder. But actually I'm adding AX squared plus BX plus C, so I can actually do that with just an adder as well. So that's a bit more efficient again than building a whole ALU, and I get out my Y. Okay, so this is kind of the other extreme. The processor is, my simple processor is like very little parallelism, do everything one after the other, but you know, my hardware is fairly simple. A register file and the ALU controlled by an instruction stream. Now my hardware is bigger, right? I've got 3 multipliers and 2 adders, but it's parallel. It's doing everything all at the same time. I put an X value in here, and a Y value comes out there, basically all in the same clock cycle, or in one clock cycle. I haven't put registers here, but I should have a register there, a register there. Okay, so this is intrinsically parallel. And we call this a spatial computation, because it's like we've laid it out in space, in two-dimensional space. So the operators, like the functional units, are spread out. Also, the state is spread out. Like you notice there's no register file here. So these state variables that were kind of all stuck in one register file before, and we could get out of them, you know, kind of 1 or 2 at a time, they're all in different spots now. Like my temporaries are just on these wires. So they're right by the functional units, and they're distributed across my chip. Okay, so it's basically, so it's not just that we have multiple operators, like hardware units, it's also that we have no central state. And then the last thing we did here is these adders instead of ALUs. So because we're not reusing things for multiple purposes, we can make our operators more specialized, which makes them smaller and faster. Okay, so for one, if I sent in one X and I got out one Y, which of these do you think is faster? And I haven't really given you enough information to answer that, so you can take a guess, right? Like, so this is one of those ones where you go, there's no real wrong answer because I haven't put any numbers on anything. But what do you think? Yeah. Yeah, the hardware will generally be somewhat faster. Why is this faster for one number? Yeah, yeah, that's a good answer. So when I look at this, you have to think, well, how fast can I clock this? So you go, what's my longest path through this? And multipliers are slower than adders, so I'd expect the longest path to be through these two multipliers and this adder. So two multipliers, two multipliers, one adder, and whatever wiring is in between them. And the wiring now matters a lot. Here, I've got to go through 5 clock cycles. Each of them is an ALU and a register file access. So I've got to read it. I've got to compute something. Maybe I can overlap the write back with the next read. So maybe that doesn't count, but at least I got to read it, and I got to go through the ALU. The ALU sometimes is doing a multiply, sometimes doing an add, so I got to kind of make my clock cycle long enough for the multiply plus the register access, and I got to do it 5 times. So that is going to be slower. I'll get some speed up from this, but I'm going to pay something for this, right? I'm going to pay area. Maybe it depends how big the control unit was. If the control unit to decode instructions, etc., was reasonably big, maybe I don't pay any area. But if I gave a more complicated computation here, this is going to keep growing, and this is going to grow slower, because all I need is kind of more memory and maybe more registers. So this is quite space efficient, but yeah, this is going to be faster. But maybe from what we just said, maybe it's 2 or 3 times faster, right? This was 5 register accesses and 5 multiplies. This was like 2 multiplies and an add, so maybe it's 3 times faster. So can we optimize this hardware? Like, and not for one number, okay? So if I want to just take one x and compute one y, this could be hard to optimize further. And to be honest, probably doesn't make much sense, right? If that's your whole computation, then you should build the cheapest processor you possibly can, because your performance requirement is so low. So let's think more like some kind of machine learning or communication system where you've got a huge stream of numbers and you're doing a calculation on them. So we want to go a lot faster. So let me erase this. Okay, so how can I make this? Okay, so let's basically say this is a stream. Okay, so let's say we'll just put brackets on this to show basically a whole sequence of data, a long sequence. Millions or billions of numbers are going to flow through here in a long stream, one after the other. And that means it doesn't really make sense unless I think of registers being here, right? So every clock period, I send a new X in and a new Y comes out. So how can I make this faster?
Pipeline.
Yeah, so I should pipeline it. So how many people here are familiar with pipelining? Okay, so how many people here, is there anybody here not familiar with pipelining? It's fine, tell me, okay? So we've got a few people, and then we also have a few people who are super shy. Who's super shy and is never going to put their hand up, so I should just remove you from the denominator. It's a trick question, you wouldn't put your hand up anyway. So I've never managed to figure out a way. There is some unknown denominator who will not answer, but I do not know how to figure out the denominator. Yeah, so we want to, we're going to pipeline this performance. So we're going to call this now streaming hardware. So this is a very, we'll talk about it next week, but this is a very useful programming model. If you think of streams of data flowing through hardware, it's very efficient. So if you can organize your computation that way, it can be a really good way to do signal processing. So, but conceptually, it's not very hard to think about. It's a stream of data that flows through some hardware. Okay, and we're going to make some changes here to try to make this faster, and a really useful optimization in hardware in general, but also is particularly effective in FPGAs is pipelining. So we're going to pipeline for higher performance. Okay, let's see. Maybe I'll draw this. Yeah, I'll draw this on top of it. I think this diagram is neat enough that I can do it. Okay, how would you pipeline this to get high performance? Yeah.
Maybe put a register stage at the output of every computation, especially on the
Okay, so so I'm going to. This was, I said, the critical path. Yeah, and what pipelining does is if we've got a whole stream of data, we're going to try to put pipeline registers in so we can clock it faster. We want this path to be not this long path between two registers. We want much shorter paths between registers to let us clock it faster, right? Because all you guys remember this, but you can only clock as fast as your longest path in the circuit. So I want to make that longest path shorter. So what do you want to do? You're saying put a register on the output of every functional unit, I think. Okay, put it on every multiplier. So okay, I'm going to put a register there. I'm going to put a register here. I'm going to put a register here. Okay, so I put 3 registers in there.
And you might also want to put a register on the I to
Here? Right. Okay, so I'm going to put a register here as well. And let me think about this for a second. It looks pretty good. Okay, so you said first put the registers here, here, and here, and then you decide you want to put this one here. Is this one good for optimization, or is it necessary?
This is necessary. That's because you want to, that's I guess the minimum delay you're going to have on one side. You're going to have to match it on the other. So that's the
Yeah. So this is a good pipelining, right? My critical paths now are short. I maybe have a path from there to there. I have a path from here through this. Maybe that's my longest path now. But that's a lot better, right? One multiplier, maybe a reasonable amount of wiring. It's hard to tell until I go through physical design like placement and routing. So it's quite a bit faster. When you're pipelining, this constraint that we'll go through again a little bit more next week. But when you basically have to balance the latency of all the paths through your circuit. So when you put a register here, I have to also put a register there, okay? Or somewhere, right? If I put a register on this left branch, I have to put another one on the right branch. Otherwise, when I do this addition, the two things I'm adding are out of sync, right? Like I'm adding something that came from X0 with something that came from X1, and that doesn't make sense. That's not what my original circuit did. So yeah, there are constraints on pipelining, and the basic constraint is you have to add the same amount of latency to all the paths through your circuit that come to an output. But we'll go through a few more examples of that like next week. So yeah.
Would you consider adding registers between, let's say, A and the multiplier, B and C, just so that on every clock cycle when you're registering the same index?
Oh, you're saying A? So A is a constant in my design, so it doesn't matter. If A was a stream of data, then I should put a register here too. So if I had a whole bunch of different A's, I should do that. But I'm assuming these are just constants. And that's another thing that FPGAs can be good at. If this is a constant, you can just essentially compile it in, connect these registers. There would be registers holding it, but they'd never be clocked essentially. They would just be sending their data permanently to this multiplier. The compilers can even do a little better than that. They can actually create essentially constant generators that just are hooked up here and just never change. If this was something that changed every clock cycle, there's a stream of it, then you're right. I need to put registers here too. Does that make sense? You might even go further. So basically, to make this as fast as possible, you could put more registers here. You could put registers there. And if I did that, I just added a register on one input of this multiplier. I've got to add a register on the other input. And then I've made this latency through the left branch bigger. I got to put it on the right branch. So, but I could put these registers in to basically isolate wiring delay. If you think your wires are really fast, what I did just wasted area and power. But usually wires are not actually that fast anymore. So it can actually be quite useful to double register like this. Like I've basically got registers before my units and after my units, and that isolates my interconnect delay as well. Yeah.
Depending on the width of the multiplication, we could also break that apart using algorithms that.
Yeah, you could take the multiplier and break it into pieces. I guess you have to put them back together. You have to have adders to put them back together. So I guess if I built a multiplier out of, I guess what you're saying is you could go inside the multiplier and put pipeline. Yeah, so you're right. If I want to, I could go inside this multiplier and basically put pipeline registers in the middle of it. And when I put those ones in, I have the same constraint. I got to make sure that every path through this register goes through exactly one pipeline register if I start putting registers in the middle of this. And yeah, you could do that and go even faster. Okay, so what I've got now, let's call this whole thing, give it a name. Okay, so we'll just define this to be operator gamma. Okay, so I made a hardware unit. It's kind of specialized. It does this quadratic equation. We'll call it gamma. I've cut its clock cycle time by pipelining it very aggressively. And if I have a whole bunch of numbers to send in, yeah, I can send them in one clock after the other, right? The processor needed basically 5 clock cycles to compute something. This one only needs 1 clock cycle, and this clock cycle now is probably quite short, right? With all this pipelining, it's down to the delay of a multiplier, which will be considerably faster than the register file plus ALU and multiplier that was in the processor. If I want to do a more complicated computation, I can keep composing operators. So in software, you compose operators by basically subroutines, right? You make a subroutine that maybe did that quadratic equation, and I might call it gamma, or I might call it quadratic equation if I was a better programmer. And then I could have another function that calls that sub-function, and I could build bigger and bigger computations, right? So everybody's done this. That's how we compose things in software, is with subroutines. So we can compose things in spatial hardware as well. So we have this stream of x values. Okay, so it's coming in 1 clock after another. And I can basically say, well, I need some operator alpha that does something. I basically produce, let's rename this alpha because that's what I did in my notes. So I'm going to confuse myself. So let's call that operator alpha. So, and that produces this y value that I just showed you. But let's say I'm not done. And this is pretty common in signal processing systems. Like if you look at a wireless communication system, there's just a huge amount of filtering and error correction and encoding, et cetera, that's going on, and all the data coming off the antennas at very high rates. So this might be one block if I have to do something to it, but I'm not done. So I might take it out of that and put it through another operator, does some other mathematical transformations. We'll call that gamma. And maybe this same interim result goes to another operator beta, and that produces some output. So the way I've done this, I basically am just making my hardware bigger. I've composed it by taking this hardware unit and saying, well, I'll just wire it to other hardware units, and I'll build them too. And I get, every cycle, I can put a new piece of data in, and now I'm actually getting 2 outputs out, but I'll get 2 outputs out every cycle. So I've got a natural way to increase parallelism. If I can describe my computation as just a cascade of operators like this, I can map that into this kind of streaming hardware. Okay, so what I just did, I increased parallelism. Let me erase this. And there's no central storage bottleneck. Yeah, because all my data is still essentially distributed, right? All my temporary results are on wires and in registers that are right by the hardware that's going to process them. And if I compare this to a processor, if I took my simple processor and I composed these bigger operations, I basically have a longer instruction sequence, right? Multiple subroutines calling each other. So it'll slow down, and I'm going to need more temporaries, so I'll get a bigger register file. And that bigger register file will take more power and will start to tend to slow down. Register files and memory in general, as you make them bigger, they tend to slow down. So that all sounds good, but there's a downside. So what have I kind of mentioned this already. What have I paid to do this, though? Yeah. Yeah. I paid area. So the processor is paying time and is paying with a slower and bigger central storage. I'm paying with area. And this may run out of gas at a certain point, right? If I keep doing more and more complicated computations, eventually this may become big enough that it's like, well, it's too costly, or maybe it's not even manufacturable. I can't actually fit it in my FPGA or in some hardware that I'm making. So that's why there's no one answer to this, right? These are like kind of tools. This isn't the only way I can map things to different hardware units, this streaming paradigm that I just showed you, but it's a particularly efficient one for a lot of the places where we use hardware acceleration. So it's a good compute model to think about.
Yes, so we also
this tends to be pretty good in interconnect power. I mean, you're right. Like as I add these units, I'm also adding wires between them. The nice thing is that okay, say how a designer would actually do this in an FPGA, and it's not that different in a custom chip like an ASIC. You would describe this in HDL, usually, maybe in high-level synthesis, but usually in hardware description languages. And you'd push a button, and the CAD tool would turn it into little bits of circuitry and decide where to place them all and how to wire them together. That CAD tool's whole purpose is to try to keep the wiring short. So it can't do it perfectly, but generally these wires will, like on average, these wires will be relatively short, so that they're still pretty energy efficient and still pretty area efficient. Like not always, right? Like maybe your computation is such that the wires get long, or maybe the CAD tool did a bad job, but usually this stays pretty local as the design gets bigger. Whereas the memory getting larger as you cascade more and more subroutines, I guess if you don't have many temporaries, that might not happen, but usually your memory will have to get bigger. And your memory fundamentally does get slower as it gets bigger. So yeah, I don't know if that answers your question or not. You usually have better operand locality with this style because you're keeping your state essentially on the wires and in the registers right within the compute units rather than in some central thing. This is a recurring theme in computer architecture. Because I'm talking about a register file is relatively slow and high power, but it's way better than going out to like a big cache in a processor, and that's way better than going to main memory. So basically, as the memory gets bigger, it gets slower and it gets more power hungry. So that's why processors try to keep the data as close as they can, but this keeps the data even closer. It's like right on the wires, right on the registers embedded in the compute units. And there are a bunch of papers now that show that you usually spend more energy, and energy is really important, on actually moving your data around than actually doing the computation. Okay, so there's no one answer to this, but that's a good rule of thumb, that you'll spend more energy moving it. This kind of spatial hardware is very good at just not moving the data much. The data is moving it to the next thing, which the CAD tools have tried to put right beside you. And that's very good. And like the worst thing is dump it all out to DRAM and bring it back in. And then there's levels in between that. Yeah.
I guess this is a follow-up question to like interconnects. Do FPGAs have different kind of interconnects? Let's say your design is too large, so the tool has to place it far on the fabric. So is there kind of like a higher metal layer that the FPGA can take to route it?
Yeah, they do have all of that.
Okay.
So we'll talk about that later in the course. So yeah, it's a good question. It's kind of looking ahead. When you're designing the FPGA, you have to prefabricate everything, and you find that some connections are long, so you build some fast routing for them. That's kind of optimized for long distance. And what that means is you actually push it high up in the metal stack, and you don't have much programmable switching on it and so on. And yeah, there's all sorts of trade-offs on that. But yeah, you do. It's exactly what you try to do. Okay, so I just showed you the streaming hardware. It looks pretty good, except it's big. So what are its downsides? So negatives of streaming hardware. Okay, so we shouldn't make everything out of streaming hardware. So we talked about one of them, which is the processor is very area efficient. So processors are very good at reusing hardware. Especially simple processors. You take a simple processor that's not building all sorts of complicated logic to try to extract parallelism from the instructions. As you make your computation more complicated, it just keeps reusing the same data path, and all you need is a bigger instruction memory somewhere. So that's very space efficient. Much more space efficient than building more and more operators and hooking them together. So it depends what you need. If you've got a computation that's not that high performance, and it's complicated, it's got a lot of steps to it, this is a pretty good trade-off, right? So you probably want to do that. Another reason, so we're just going to rotate up here, like what if my performance requirements are low? So not all computations have to go really fast. So maybe you're in an embedded system and you've got to you've got sensors bringing data in, but it's not coming in very quick, then you're cost optimized. You just need to keep up. A processor is probably fast enough, and as I said, especially if there's a lot of steps in the algorithm, it's very area efficient. So maybe this would be faster, but you just don't care. And there are a bunch of systems like that. So then you just want to cost optimize it. So there's a last case where streaming hardware is not that good. That would be if you have serial computations, like you have a serial algorithm. Okay, so you don't get any speed up then. Okay, so a basic processor does serial decisions. If your algorithm has a whole bunch of if, then, else in it, that's fundamental to your algorithm, it's actually a pretty good match to a processor. Here I'm basically doing a computation that's called a feed-forward computation. So I send data in, and I don't actually have data go backwards and get reused, and I don't have any decisions either that I have to make here. I just do the same thing to all the data. So it's intrinsically very parallel. If I had an algorithm where it was like, look at the data, and every step I had to make an if, then, else decision, you can put that in spatial hardware with a whole bunch of muxing to choose this or that, but it hurts its efficiency. And it's a very good fit to a processor where it fundamentally is making its decisions instruction by instruction. So there are a bunch of things that fit well to processors. Let's see. Okay, so I just said that streaming hardware has its strengths, processors have their strengths. Should I make a mixed device? Okay, so what do I mean by a mixed device? I mean, find the high throughput computations that I need to do and put them in streaming hardware. But usually in a system, you'll have some control logic, some error conditions, some setup, like various other things, some unusual conditions that is less throughput intensive. Might have some serial algorithms, other things that are low performance. So I can put those on a microprocessor. Okay, so I can make a chip that's basically a mix. Okay, so maybe I make some streaming hardware here. And streaming hardware is more specific. The hardware I just showed you was doing the quadratic equation, and that's all it did. So I might have more than one kind of computation that I need to do. So maybe I need to make a few different streaming hardware units because they're more specific. So maybe make 3 of them. And then make this microprocessor to handle everything else. Because, yeah, there's some stuff that's serial or low performance. Also, there may be some stuff that I didn't think of, and it's kind of dangerous. So I made a chip, and all I could do is these 3 things. And it turns out there's a new feature that the market requires, and I have absolutely no way to do it. So what do you think? Does this hybrid thing seem like a good idea? Okay, people are nodding. So yeah, this is what most modern ASICs look like. So most modern ASICs, and everybody know the term ASIC? It's like a customized chip, right, that you fabricated, does one thing. It's too dangerous to make it do literally one thing. Like you do streaming hardware 1 and nothing else, that's generally too dangerous to do now for an ASIC, because you better be really sure that you got it exactly right, the market doesn't change, the standards don't change, etc. So that's pretty risky. So usually you won't do that. You'll do something like this, where you still leave some programmability in from the microprocessor. It's also the way most big FPGA systems look. Okay, so we'll talk about this in a minute, but in FPGA, because you can reprogram it, you could change the streaming hardware unit. So you still have the ability to respond if the market changes or you made a mistake. But even then, usually it's a bit dangerous for a big system to put everything in streaming hardware. You usually wind up with some microprocessors right in the FPGA chip doing some of this low performance stuff. In ASICs, though, there's even more pressure to put more of the stuff in a microprocessor because you can't make any changes to these things, so more risk. Okay, so we spend some area to get flexibility. But you still have to make a lot of decisions. So if you're going to make an ASIC, a custom chip, you still have to choose a lot of things. Okay, so we have to pick what are these stream units. Right, so my specialized accelerators. And you don't have to do one, you could do a few, and maybe you'll wind up not using some of them in most or maybe even all applications. You made a mistake. You can't put 300 of them in. Like theoretically you could, but now your chip is not economically viable. So you do have to make some decisions of like how many of these things can we put in, what are they? And you have to commit those to silicon if you're doing a custom chip. And you have to decide how to connect things. Right, so we have to decide how to connect these hardware units to each other, how to connect them to the microprocessor, how to connect them to I/O and DRAM outside. Okay, and one way we could connect them is we could say, well, maybe they'll all connect to DRAM, and all communication will go through DRAM. It's very flexible because we said it's like central storage. Everybody can write to DRAM, everybody can read from DRAM, but it's going to be a bottleneck. Right? A lot of times they're going to be waiting for DRAM because it's busy. It's also high energy. It's high latency. Like it takes many clock cycles to talk to DRAM. So that would be very flexible, where we say, let's just use central storage. Everybody talks to DRAM. Everybody reads from DRAM, but it's inefficient. So you probably don't want to do that. So you're probably building some wiring between these things. And you're probably making it can get large if you say, well, they can all talk to each other in some giant crossbar. Right? Like we won't make any decisions again. We'll say they all go through some crossbar so everybody can talk to everybody else. That also gets large. So you have to make some decisions on how you're going to wire them together. And if you make them well, your system is efficient and kind of just programmable enough. And if you make them poorly, you lose efficiency, or you can wind up with a system where things can't talk to each other well and you can't sell it. So you have a bunch of difficult decisions to make still. So we could do central storage. Right, that would be one extreme. Put everything in some big memory, maybe DDR. So it's flexible, but inefficient because it's a bottleneck. And then the other extreme, I could pre-decide on exact wiring. This talks exactly to a certain port on the microprocessor, and this output goes to exactly one input on this hardware. That's much more efficient, right? Again, I'm getting local data that's just being communicated. But you better get it right. If it turns out that your data doesn't go to the right spots, your system might be somewhere between hard to program and use efficiently to impossible to use for your application. All right, so let me just write that down. So that's your other extreme is fixed connections, which is efficient, but it's inflexible. Okay, and there's a whole world of trade-off space in between these things. I could put some ability to, some muxing basically, in my interconnect, and that makes it more flexible but less efficient. I could write into some memory buffers, but instead of making one giant one, I'll make more special purpose ones that are smaller. And each of the things is, kind of in between these two extreme trade-off spaces. So, I think what I'm going to do now. Okay, so the next thing I'm going to talk about, that's kind of why. Hopefully, there's a reason why people don't just put everything in processors, okay? But there's also a reason why people don't put everything into, streaming or hardwired logic. They both deserve to exist, and most systems combine them in some way. The next thing I'm going to talk about is, well, why do we use FPGAs? Okay, because we've talked about processors and we've talked about fixed hardware units. I can make fixed hardware units in a custom chip called an ASIC. So maybe the world should only have ASICs and microprocessors. And I say that that's not a good world, right? Because I think I no longer exist in that world, or I have to change myself a bunch. But that's not a good reason. I'm going to try to give you other reasons why it's not such a binary choice, right? So FPGAs also fit in there. But those reasons are a little different. We need to start looking at some economics. If economics was not a factor, then you probably never would use that FPGA. You'd be like, well, the most efficient solution would be sometimes use a processor, sometimes make a custom chip. But economics means that is not always feasible or economically rational. So why don't we take like a 10-minute break, and then we'll come back and we'll talk about that. This class is scheduled for 3 hours. My goal is to rarely go 3 hours. Instead of going late, if I scheduled it for 2.5, I go early for 3. So I've set the metrics, I think, better. So let's take a 10-minute break and then come back. Can you hear me okay, Sahil? Okay, sounds good. Actually, Sahil, what works better? Does giant chocks work better, or should I try the small chocks? It works better? Okay. All right, sounds good. Okay, so hopefully I've convinced you that there's a world for both processor-based systems and more streaming hardware or more focused hardware system. So let's talk about FPGA versus ASIC. Okay, ASIC means application-specific integrated circuit. So it's a custom chip. And the idea is it's less general than a processor. You could call a processor an ASIC as well, but it's so flexible that it's just a kind of basic processor. We don't really call it an ASIC. So it's basically more focused on some area, and more efficient than a processor for that area. Okay, so let's say we've decided we want more than a processor. We want some more specialized hardware. So now our decision is basically only 2 ways to get customized hardware now, right? So we can build a custom chip, an ASIC, or we can buy an FPGA. Right, so with an FPGA, we just buy it, choose one, start programming it, and we can sell it. With an ASIC, we have a much longer procedure. So we have to design it, we have to verify it pretty carefully, do a lot more simulation. We have to manufacture it, so we create masks that go off to some foundry, which nowadays is almost always TSMC. They make it. It takes them about 2 months to send you back the first chip, and you get that chip back, and you have to test it. So you actually have to design test patterns. You have to figure out, like, well, how am I going to test this thing, right? So I got a chip with, like, I don't know, 10 billion transistors in it. What is my strategy to test it? So I have to make those tests. I test it. I see if it works. I actually need to do some qualification. It's going to work for a while. Transistors are subject to all sorts of aging effects now. So I actually have to do some burn-in tests to make sure it's going to keep working for a sufficient amount of time. And then finally, I can sell it. Okay, so there's a much longer sequence to build an ASIC, because the design cycle is longer, it has many more steps in it. Instead of like programming an FPGA and just testing, does this work, which a lot of FPGA designers will do, right? So you should use simulation. You shouldn't just you don't take a big design and just program it in the chip every time. You simulate, you make sure you think it works. But once it looks like it probably works, you can actually just program it in the system and now see if it works in the system. And you're testing it at maybe 1 million times the rate. So instead of testing it for 1,000 clocks, you now tested it for 100 billion. And it fails, and then you say, okay, let's figure out where it failed, and let's go back and debug my HDL, and let's compile again. That might take, for a small design, tens of minutes, for a big design, hours, but then you can program it and try again. Okay, for an ASIC, every mistake is like root cause analysis. The chip took 2 months to come back, a root cause analysis after your tests fail, which takes a while. Then you figure out how you're going to change it to fix it. You're not going to just say, I think this is the right fix. Let's just basically spend a whole bunch of money to make new layout masks, send it off, wait 2 months, and we'll see. You're going to do a lot of verification again, and you're going to send it away. So the whole design cycle is much slower with an ASIC, and it's much more expensive. So what this means is that the ASIC is smaller, right? An FPGA has this programmability. We're going to talk a lot in this course about how it gets it. But in an ASIC, if you want to do something, like you need a 64-bit multiplexer, 4-to-1 multiplexer, 64 bits wide, you build that, right? You write that in your HDL. You will get the exact gates to do that. You will have metal wires connecting all of its inputs and its output to the right spots. In an FPGA, you don't get that, right? You get some programmable logic that can be programmed to implement that multiplexer and some programmable routing that has switching in it. So it actually has more multiplexers just to connect signals to the right spot. And it has prefabricated wires. So that programmability costs, right? It's not as efficient. Okay, so what does this mean? It means the ASIC is cheaper in high volume. We'll get into some estimates of how much cheaper. It depends a bit on what you're doing, but it's significantly smaller and significantly faster. Okay, it's not percentages, it's like factors. Okay, so you get a much more optimized device if you put it in, design if you put it in there. But it needs this custom manufacturing. Okay, so it needs a more complex design flow with many more steps, and it needs custom manufacturing, which takes a lot longer. Okay, so there's a trade-off point here. If you have an infinitely big market and you have infinite time to optimize, you should always do an ASIC, right? It's like the asymptote, most efficient solution. But let's try to figure out, where this breakpoint is. Okay, so the cost of an ASIC is in design costs and in time to market. Okay, so what's the break-even point? So this is hard to answer, right? It's going to depend on how efficient was your design team, how big is the chip, therefore how hard was it to design, what process technology are you targeting, which affects like how expensive it was to get this custom manufacturing done. But so we'll just pick some representative process technology and kind of walk through to get like an order of magnitude. But you should not go off and say it's exactly this number, right? So it's going to vary depending on exactly what you're doing. Yeah.
There's a bit of, I guess, or at least I heard that, I think many years ago now, there's a survey done by, I guess, within Professor Lewis's group on the quality gap between FPGAs and ASICs.
Yeah.
And I think, I don't remember the number off the top of my head, I think that time was like 4x, but I was curious what you would think the sort of the quality gap would be now.
So his number wasn't 4x, okay? And we're going to actually talk about that paper. It was much bigger. Well, he got one number of 4x. He did it a few different ways. The 4x is when I asked him to do it a different way. Yeah, I remember when Ian Kwan, his PhD student, I was still in Altera at that time, so a student presented at one of the main FPGA conferences. And yeah, the number he came up with was 40x, which is, if you have a small design and it's all kind of the programmable logic, doesn't use any of the hard blocks, is probably about right, But it's not right for big designs that use a bunch of the hard blocks and so on. Anyway, it's interesting because it was like you go to a conference with like 300 people there and you call their baby ugly, right? So, Ian Kwan's he's a brave engineer, right? But he had his data, which is good, right? So he gave the "you want a piece of me" presentation. So we will talk actually about that paper and a few other ones to try to quantify that gap. But here I'm kind of just going to go, just take my word for it, it is factors, okay? So it's not percentages. You are losing a lot of area and a significant amount of speed too, but not as bad as area. Okay, so where's my break-even point? How big does the market need to be? So let's just put some numbers in to get a sense of the magnitude. So let's say I'm going to do this in 22 nanometers. The FPGA that you're going to use for your assignments is 22 nanometers. It's not cutting edge. You can go smaller than that, but that's what we're going to do because the licensing is a real pain. And if you're doing an ASIC, it's actually a lot easier to do a 22 nanometer ASIC, which is not absolute cutting edge, but it's also not a crazy old process, right? Companies like NVIDIA will be doing 7 and 5 nanometers, but this analysis would point you to, you need a really big market for that, okay? 22 nanometers doesn't have to be quite so big. But that's part of what changes this. So at 22 nanometers, you get different estimates from services like DataQuest of what does it cost to do a design. But typical numbers would be $60 million to $100 million. Okay, so it's a lot to do an ASIC. Now, if you've got a really efficient design team, or your design is also like less complicated, you could bring it in probably somewhat underneath this. But this is like a realistic range. So, where does that cost come from? One that's really easy to quantify, but it's not the main cost, is masks. Okay, so the masks alone. Everybody know what I mean by masks? Okay, does anybody not know what I mean by masks? Okay, so the way that semiconductor manufacturing works is you have to have lithographic masks that are used when the optical cameras basically project an image on the wafer, and then you have photoresist that reacts to where it's exposed, and you can chemically remove the photoresist where it was exposed, for example, and now you can use it as a mask to, say, remove the metal that was in the spots that you exposed to light. Okay, and you do that, there are many masks, right? So there's like maybe a 22 nanometer process might have 50 masks to make all the pieces of transistors and all the pieces of metal and so on. And especially the masks for the transistors and the first few layers of metal have to be very high quality, okay? Like they are very small features that are down smaller than 22 nanometers. They also, the wavelength of light that is being used for these chips is typically more than the feature size. So there's a lot of processing of the actual what you want to put on the chip through very expensive CAD tools to do optical pattern correction to basically make a pattern that will result in what you want showing up on the chip. Those tools are expensive, they take a long time to run. The masks that are manufactured actually have flaws in them, so the mask maker has to actually go in and make some changes. Like, it's all really expensive, okay? So think of really complicated, really expensive custom manufacturing. So if I want to get a mask set for 22 nanometers, it's about $2 million. And you need one of these every time you change the chip, okay? So if I make the chip, and then it comes back after 2 months, and I test it, and it doesn't work, or it works partly but has a flaw. I figure out that flaw, I verify a lot to make sure I got all the flaws, and then I make new masks. That cost me another $2 million. So obviously every ASIC design team would like to just make one set of masks, but on average they need more than 2. Okay, so a good team would need 2, fantastic team would need 1. Okay, so I was part of many Altera tapeouts. We, on average, needed more than 2, okay? So I guess I can't speak for the whole industry, but like, there was like one particular FPGA on where we're up to like stepping F or H or something, right? You're like, whoa, that's a lot of masks. Sometimes you can fix things without changing all the masks. Maybe you just change some of the metals, that's a bit cheaper. But on average, you're gonna use 2 or more full mask sets. Okay, and the cost of these go up very rapidly with process technology. So let's say you go, I don't want to do 22 nanometers, I'm gonna do something that's like 7 nanometers, which is quite close to the cutting edge. Okay, so that's about $10 million for each set, and on average you're going to need, your design is actually more complicated, there's more things that can go wrong, so probably this 2 is too low as well now, but it's harder to quantify, right? Maybe you get lucky. But you can see these are pretty big numbers, and you can't avoid them. You got to make masks. But this isn't most of it. You have a complicated design cycle that has many more steps than when you're mapping something to an FPGA. The CAD tools are expensive. A license Yeah, I don't know if I can actually get that. Okay, so a license at a major semiconductor vendor for 1 year for a place and route engine for a full custom chip was $1 million. Okay, so the CAD tools are very expensive, and you need multiple licenses of these CAD tools. You need a lot of engineers, you need a lot of verification. You need to have product engineers, so when this thing comes back, they're doing the testing, etc. And in an FPGA, you don't do any of that. The FPGA vendor does it, so these numbers are too low for an FPGA. So as part of many FPGA designs where we're actually making the next generation FPGA, we could not make a next generation FPGA family for $100 million. It was many hundreds of millions of dollars. Now, an ASIC actually typically is not as complicated, so it is cheaper, but these numbers are reasonable. And you'll find them in all sorts of data quest surveys and so on. I mean, Google, when they did the first TPU, they said they had an amazing design team and they pulled it in for $30 or $40 million. So maybe some amazing design teams can do it somewhat less, but you're not doing it for $3 million, right? Like you could say, I'm amazing and I think I can do it for 40. So, okay, so that gives you some idea of the cost. Okay, so does that mean we need a market that is at least 60 or $100 million? Who thinks that means that? Okay, Alex thinks he needs that. Do not invest in Alex's company after he graduates from here. Okay, Alex is a great student. Okay, but he should be CTO. Do not make him CEO. Okay, so no. Okay, so a typical model for a high-tech business, so one where they're kind of at the cutting edge, they have to invest a lot of money in R&D, is that you can spend 20% of your revenue on R&D. Okay, this was our model at Altera. We were a pretty research-intensive company. Some of our customers were a bit lower than this. There weren't many that were higher than this. Okay, so 20% of your revenue on R&D. Okay, where does this come from? Well, if you spend all your money on R&D, then how did you pay for the actual chips, the packaging, the marketing people, and where is your profit, right? And the building, etc. So if you spend 100% of your money on R&D, you are a university. Okay, and you are not going to turn a profit, right? So this is pretty generous, but that is a 5x multiplier. So if I do that on the $100 million, let's just stick with that for simplicity, I'm up to $500 million now. If you've noticed that there's an opportunity, like there's a business opportunity for some chip to sell $500 million worth, you're probably not the only one. Right? There are probably other companies that have also noticed this, or it might be the next generation of a product and there are competitors. So probably there are other people chasing this. So let's say that your business model is that you think you can get 20% market share. Okay, so if you do that, now you need a $2.5 billion market. And that's not in 1 year. It's kind of over the chip lifetime. So if you think this market's going to last for quite a few years, it doesn't have to be $2.5 billion a year. Maybe it's $500 billion a year for 5 years. But most markets nowadays don't last that long, right? So maybe 2 years is a bit more realistic. So there definitely are markets this big. There are markets that are a lot bigger than that. So if you're Intel or AMD and you're making the next generation x86 processor, your available market is, at least tens, probably hundreds of billions of dollars. You are going to make an ASIC, right? You're not going to say, I want to save the NRE, we'll put it in an FPGA. If you're NVIDIA and you're making AI accelerators, your business opportunity is definitely in the hundreds of billions of dollars for the next generation chip. So you're gonna basically for sure make it custom. But there are a lot of markets where this doesn't look so good. Right? Like you start getting below this number and it doesn't make a lot of economic sense to do an ASIC. You need to start thinking, maybe I won't have that much competition, et cetera, but that can get a bit dangerous. So, so this is over the chip lifetime. Okay, so to pursue these things, you need to be chasing a big market, and there are lots of markets just aren't that big. So that's your first thing. Okay, so the first one is the non-recurring engineering cost. How much is it going to cost me to get that first chip, and what kind of market does that restrict me to? It restricts you to fairly large ones. Again, this is not a perfect answer. Like, let's say you were doing a very small device in a very old process. That will be a cheaper design. The market could be smaller because your design costs will be lower. So if I was doing this in 90 nanometers and I was putting it in a kid's toy, it's a very small device, then I might be able to make it work for a much smaller number, and the market doesn't have to be as big. On the other hand, as your performance requirements get low enough, you could just buy a processor. So at that point, you may go, well, maybe this doesn't make any sense, right? I'll just buy a processor because it's good enough. Okay, second thing is, well, let's see if anybody can guess it. And if you looked at the slides online, you can be a great guesser. So like there's a pro tip of you could be the world's best participant in this class if you just read the slides in advance, right? So, okay, so this is one thing you gotta check, non-recurring engineering costs. What's the other thing you should check? Is there anything else I should worry about? Yeah. Yeah, I guess I'm bundling that in here. I mean, you're right. I guess maybe I didn't put that down, but it's another idea of you may not know how to do some of this stuff. You may know how to do the design, but yeah, let's take the FPGA companies. They have whole product engineering teams that make sure that the chip is reliable. They have software teams that have made sure that you can program it. If you make your own chip, and it has some programmability in it, usually it will. It'll usually have a microprocessor in it and so on. You got to build a software stack to make sure people can use that chip. You have to have product engineers to make sure it's reliable, not just you tested it and it worked the day it came off the factory floor. You're guaranteeing it'll work for 5 years. How do you know? You actually have to do accelerated lifetime testing. You have to make sure it's still robust enough. You may not have anybody who knows how to do that. So you're right. You have to build that kind of infrastructure. And even if you have them, they cost money. So. But there's one other fundamental thing you have to think about. So yeah, what do you think? So yeah, so per unit costs, which I've left out, that's basically over here. That's the reason to go to an ASIC. And we'll kind of try to quantify that broadly in a while. But the per unit costs for an ASIC are much lower. Depending on what I'm doing, they could be 5x to 10x lower, right? Even 20x. So I can win a lot on per unit costs. So if this market was $100 billion, where you kind of go, it's worth chasing for sure. That unit cost advantage is enormous, and you should just do the custom chip. You got to optimize it to the hilt. Yeah.
I was going to say, when you do logistics, you're going to be buying your chips in China. You're going to have to figure out how you're sending it everywhere. You have to figure out, is it a working chip, all that process.
Yeah. Now, I did include that in this number. So this is including, you're working out the packaging, logistic. You have to package it. You have to work out if it works. So it's in there, and it does affect your costs. But there's one other thing it affects. It's not just about costs. Is there anything else you should worry about? Yeah, but I've kind of put that in here too, right? The FPGA comes pre-tested. The FPGA vendor worked it all out for you. The ASIC, it's your problem. But that's part of where this comes from. You have to actually have test engineers. Your design verification is way more complicated. So that's kind of baked in this cost. That's a good question. You're right. You need to build that too. Although you might have to build some of that no matter what, right? Because if you use an FPGA and you put it in the system, you still need to support the end customer. Because you're not going to say, contact Altera or Xilinx, right, about the Cisco network router. Like, what? Do you know what I mean? So.
Time? How long is that?
Yeah. So the other key thing is time to market. Okay, so it's actually interesting. So I'm glad I asked this to see how long it took people to get this. I think it's actually something that fundamentally most engineers underestimate, how important time to market is. Engineers like to optimize. So they kind of look at this and they go, yeah, some costs, but that's more optimized. You should just do that, right? And maybe if no one will give them that much money, they'll reluctantly go, okay, fine, nobody gave me the money, I won't optimize it as much. But time to market is also super important. Okay, so I'm going to make up some numbers. But they're realistic, right? This is like, they're not rigorous in the sense of like I can do an integral and prove that what I told you is the exact right number, but these would be representative numbers of a real, what you'd really see. Okay, so let's say I'm making some product. I found my $2.5 billion market. That $2.5 billion market's not there forever. Maybe it's the next generation Wi-Fi standard or a base station encoding, or it's a new neural net accelerator that I want to get out, but other people are working on this. The neural net models are moving. This market opportunity is not going to be there forever, okay? So on the y-axis here, I'm putting revenue. And on the x-axis, I'm putting time. Okay, so I have some idea of a new product. And sometimes this new product is kind of obvious, like the next generation wireless standard comes out. Everybody knows that it's going to need all sorts of different chips. You identify one of those chips and you start working on it. So everybody knows it's coming. Sometimes you might have identified something that, it's less clear to everybody else that it's coming, but it's pretty often people know this is happening. Okay, so there's a race of how long does it take you to design it. Okay, so that's your time to market. And let's say, it took you a year to design not just like the chips. So you designed an FPGA and you designed like the board that it would go onto and the software that's going to run on that and the whole system. And you got out a card that will go in the next generation wireless base station. So you took a year. Now what happens is your customers, so my hypothetical example, they're like wireless providers, right? Like they're the Ericssons, the Nokia, Siemens Network, et cetera, the Huaweis. They're designing you into their base station. So they can be talking to you in advance, but they're not going to actually design you in and start testing that you work in their new base station until you have your chip or your board, right? So once they're designed in, the market's growing, and you're starting to get more and more revenue over time, but it only lasts for so long. So let's take cellular communications. It's not very long before the next standard comes out, or people decide to have even more antennas or an even higher data rate, I can do better. So now your standard starts to decline a bit. It's being replaced by the next generation. And maybe after 3 years, nobody's buying your chip anymore, right? They're going on to the next generation. Okay, so we got a growing market for the first while, and then we got a maturing market where it's declining after. And this is the world we live in, right? Like even 3 years is actually, sometimes it's a lot shorter than that. So it can be very fast. So let's say that you're an engineer who likes to optimize. You say, we're not doing an FPGA, we're doing an ASIC. It's going to be way more optimized to be better. And let's say your design team's quite good. So your design team, even though the problem is now harder, every time you make a mistake, it's like a 2-month delay to manufacture, but also a bunch of delay to do the root cause analysis and verification. So you're at least 2 months behind just from custom manufacturing if you make no mistakes. But realistically, it's way more than that with all these extra steps. But let's say you throw people at it because you got a lot of money, and it takes you 6 months longer to get a working thing. People don't start designing you in until they have this chip. So you start ramping later. The market still matures at the same point. So you never ramp to the same revenue, and then it starts declining. So if you integrate this, and I made these numbers up, right? But again, they're realistic, maybe even conservative. This is like a 62% revenue loss. The point is it's huge. Like being late to market is really terrible. There is an incredible pressure to go fast. And FPGAs are very good for going fast. So even though the system is less optimized, getting it earlier is generally more important in most markets, right? Sound good? I'll tell you a couple of stories about this, right? Just to make this sink in, because those who are out working may already be living this, but those in school probably massively underrate it. So one of the brilliant engineers I had at Right Track CAD, my company, and then Altera, was a graduate of U of T named Ryan Fung. He's a great engineer. He loved to optimize things. He was great at optimizing our chips, great at optimizing the CAD tools. He hated to stop optimizing and move on to the next product, okay? So he was still, when we were at, I think at 28 nanometers, he was still talking about like, I could optimize the 65 nanometer part better if you just gave me more time. And it's like, Ryan, that's 2 generations ago. Like you would be 4x behind in density and so on. It just drove him nuts that he would have to cut off things and it's like, nope, that product is done. We know we could make it better. We don't care. We're moving to the next product. And that's always the right decision. But yeah, some engineers, because of this natural desire to optimize, they don't like doing it, right? But it's super important. I worked on a bunch of different generations of chip design when I was at Altera. And one generation, let's see, this was the 65 nanometer generation actually. So we did a 90 nanometer part. It was very good, lots of new stuff in the architecture, and it outperformed our main competition, Xilinx, and we took a bunch of market share. So that was great. And I can't actually explain why we did this, but as a company, at that time, the time delay between process nodes was 2 years. That was how long TSMC and its competitors were taking to bring up the next process node. And for some inexplicable reason, we decided that we would take 3 years to design the next architecture, because we just kind of worked out how long should it take to fully optimize it, and it was 3 years. And what that meant is at the next generation, at 40 nanometers, Xilinx came out with the next generation part a year before us. And it wasn't actually because we screwed up the design, it's because we planned it that way, which actually is inexplicable. Like, I actually have no idea why we did this. So that was like, it was incredibly horrible for our sales force, because for an entire year, they were fighting one process generation behind, okay? And a process generation at that time especially mattered a lot. Their transceivers were faster, their density was bigger, et cetera. So by the end of that year, I mean, they looked like they'd been in the trenches of World War I, right? Because they're kind of going into customer after customer trying to win with a product that is just behind. We came out with that part, and we'd optimized it for 3 years. It had a bunch of quite innovative features, so we're proud of it. On metrics, most of the performance metrics, it was better than Xilinx's part. That lasted for 1 year till their next generation part came out again. It was not a good trade-off, right? Like, we lived this, you know, except it was not 6 months, it was like a year. So you're a year late, you're getting beaten up by your competitor, they're getting designed into all systems, you come up with a better product, it's like starts getting some traction, and then it starts, you know, they're on to the next system. Like, so actually for the next generation after that, our CEO said, I do not care what it takes, you will not be late, right? Like, I would like as much performance as you can get me, you can make performance targets. We had to make performance targets. He doesn't let engineering just kind of go, it is what it is, right? If you're in upper levels of engineering, your CEO does not want to hear like, we don't have any performance targets, we'll see what happens. But he was very clear of your number one task is you will not be late to this process node. Like, as the risk production, meaning we don't know if the process is really reliable yet, becomes available, you will have a design that's on there, and as that process is being qualified, you will be debugging that design. You'll be like one of the first chips off the line. And we did it, and we actually wound up being ahead of Xilinx by maybe not quite a year, but almost a year. And our sales force loved it, right? Like, I remember going to visit one customer in Ottawa, and this customer was very happy with our chip, right? They're using it for high-end memory testers, and it had very fast I/O, and it could do all the logic they needed. And I was brought in like as a technical person to talk to them. And at one point I said, we're happy with all of it except the price. And I said, what does it cost? And they said, like, it's $50,000 a chip. And I knew what this chip would cost to manufacture. It's maybe like $100 or $200. I didn't say anything because I was just thinking, like, what? So at lunch with our sales force, I said, like, what is up with that pricing? And they said, we're unopposed. Right? They said the competition has no product that can match those specifications. They need those specifications. So they said maybe we went too far because they are getting nervous about designing us out because $50,000 a chip is a lot. But anyway, the next generation, both Xilinx's CEO and Altera's CEO, Xilinx's CEO was not happy with his engineering teams being late either, right? So that generation, he was angry. The next generation, which is 28, they both gave the same mandate of you will be first to this process node. And that was a busy design experience, but it was the right message. So anyway, I guess the whole point of that long story is that even if the sort of inexplicably an entire teams of engineers sometimes lose sight of this, but then when you live it, you realize like how bad it is. Talking to the sales force and saying, they're like, they don't care, right? They're like getting killed. Are better for power, so true. Okay, so let me turn on the projector here. Okay, so last thing I'm going to talk about today is just a bit of an overview of let's start talking about what's inside them. This was like, why would I use an FPGA? Why would I use an ASIC at a high level? Okay, so what's in an FPGA? And I think probably this is a review for a lot of people, but gives maybe an overview of we're going to go a lot deeper in the second part of the course. So this will be like a classic old FPGA, and people still sell simple FPGAs like this for simple purposes. So you have IOs, you have logic that's programmable, and you have programmable routing in between them. And how does each of those work? So there are a few different ways you can make the programmable logic in an FPGA, but the dominant one is use lookup tables. So it's basically a 1-bit wide functional unit. You send some number of inputs into it. Inside of it, you have basically the truth table of the function you want to implement, and a multiplexer that is controlled by these inputs, and it just selects the right bit of the truth table and sends it out. You want to do sequential logic, so you also build flip-flops. So the simplest way you could do that is you build a flip-flop, and you build a multiplexer that you can control with a select signal. You'll program that too, so that select signal will get programmed into another SRAM cell. So now you can decide, do I want to use the register or do I want to bypass it? And what I've just shown you here can basically implement any function of 4 inputs, and it can make it either registered or not. So this is a pretty reasonable FPGA logic element. Okay, so I take that logic element, and then I replicate it. So generally, most FPGA architectures take that logic element and they group it into something bigger called a logic block, because again, we'll go through this later, but there's some efficiency advantages to grouping a bunch of these together, so you can share things like clocks and so on, rather than just thinking of them as all being distinct units. So you take that, you call it a logic block, and then you're going to replicate a lot of those logic blocks. And you could do this in lots of ways, but most FPGAs do that in columns. It basically makes the layout easier. All these logic blocks are the same width, so I can just stack them, and some signals will kind of line up nicely, so it'll fit in my layout well. And then I want to make a whole bunch of those, so I replicate those columns. I can put my IOs around the outside, and that's what's generally done in lower-end FPGAs. So like the Cyclone or Spartan series FPGAs from Altera and Xilinx. You put them around the outside so that it can be connected with wire bond technology, right? So little gold wires get ultrasonically welded onto these landing pads and connected to the package. So for higher end FPGAs, they're often put in columns and put inside of the chip array, and then they're basically connected to the package with flip chip mounting, which means you've got solder bumps, you flip the chip upside down, and the solder bumps get melted onto landing pads on the package. It's more expensive, but you can get more IOs, and the IOs have lower inductance, so you can run them faster. Okay, so one of 2 ways you put IOs in. We'll talk about the sum later, but the IOs are actually a big part of the value proposition of FPGA. I actually forgot to say this earlier on. So we actually went through all the performance advantages of an FPGA. That's one of the 2 fundamental reasons that people use an FPGA, as a processor is not fast enough. The other fundamental reason is that they need the IO. Okay, people don't think about that as much, but if I have a processor, it might be fast enough, but it has certain IOs built into it, like certain voltages, certain standards, and if that doesn't connect to the sensors that I want, and maybe the actuator for the brakes in my car that I'm putting this in, etc., or the actuators for my washing machine, I can't actually use it. It literally cannot electrically talk to all the devices that I want it to talk to. These FPGA IOs are actually highly programmable. And there's a survey paper that you'll read that talks a little bit about how that's done. But they're programmable in all sorts of ways. Like, what's the protocol? What's the voltage? What's the timing? Is it registered or not? Is it differential or not? So they're actually quite complicated to build. And that's another key value of an FPGA. Of it actually, you can put it in a system, and it can talk to like almost anything by programming the IOs. And if you look at microcontrollers, for example, there are a lot of microcontrollers, and they span different I/O standards, but they can't cover them all. There's just too many possible combinations. But an FPGA pretty much does cover them all. And I know when I was at Altera, there would be people from Altera who were on the standards committees for next generation I/Os, like PCI Express, the next generation. And because we're one of the main FPGA companies are one of the major vendors of I/O connectivity. Right? Inside a lot of systems, you'll find an FPGA that ties everything together. Talking to some of our engineers who are on those standards committees, it's interesting because they're actually a high-stakes game where various companies on there want their protocol to win, because if their protocol goes in the next generation standard, they have an advantage in terms of they're ready to go. So their time to market is better. So there's standards for some of these high-stakes things are partly technical, but they're partly political, because companies are also jockeying for advantage. So, Huawei will have one standard they've been working on. They really want that to be in the standard. And Cisco has a different one. They want that to be in the standard. And the FPGA companies were interesting because they would basically act like the peacemakers. They're like, well, I hear good points there. I hear some good points there. I think we should take those proposals and merge them. Let's just say they're both options. But that is actually exactly what plays to the FPGA vendor's strengths of like, what I want is I want programmability everywhere. So everybody's got an idea, just put it all in, right? So it was interesting. Okay, so now I need to be able to connect all these things together. So in between them, I put programmable routing. Okay, and the programmable routing actually runs basically on top of everything. The wiring runs on top of everything, but we have to also put switches in, so we have to drop down to some transistors. Okay, so how does this programmable routing work? So we need programmable switches. So let's look a little bit more about what's inside of a logic element. So let's not do a 4-input lookup table. Let's do a 2-input lookup table. Again, we'll analyze this later, but it turns out this wouldn't be a very good choice. It's not very efficient, but it's easier to think about. So if I have a 2-input NAND gate, its truth table is I only get a 0 if both inputs are 1. So I basically program that truth table into a little memory, a 4-bit memory, and I take the inputs, these A and B inputs, and I hook them to the select of this multiplexer. And then basically, depending on what inputs I send in, I just send out the proper SRAM. And my CAD tool will have read your design, figured out that you wanted to make a NAND gate, and would have programmed these 4 SRAM cells with this truth table. So you've got your NAND gate. But clearly, I could do any 2-input function, right? Just different truth table, different function. So again, it works out that it's more efficient if you do bigger truth tables. Usually like 4-input or 6-input are dominant, but this is easier to show. Okay, so that's how I made my logic element. I now need to wire these together. So if I was in an ASIC, I just wired them together with metal, right? The transistors, specific transistors are made to make the gates with little bits of metal between them. And then the ASIC CAD tools, their router will basically put down metal, put on the mount. And this is part of the architecture problem, like how long should those wires be, where are they, et cetera. And then you build a bunch of switches between them. And your simplest switch is basically a pass transistor. So a pass transistor with an SRAM cell. If I put a 1 in this SRAM cell, you put a 1 on the gate of an NMOS, and it acts as a kind of slow, not great, but wire, right? It acts like a wire with additional resistance. If I put a 0, basically the transistor's off and it's disconnected. So this is kind of the simplest programmable switch. There are other ones that people use, but this is the simplest one, and it's the basic building block that's used to make programmable routing. So you prefabricate wires, and then you put transistor-based switching in between them. And you have a lot of these. So you have tens to hundreds of millions of these bits and switches in an FPGA. So that's the architecture problem. Like, where should these wires go? Where should these switches go? And it's also why you need CAD tools. Like, so nobody is going to go off and program 100 million switches to connect up their circuit. So you need very sophisticated CAD tools that turn your HDL into these hundreds of millions of bits step by step so that you never look at it. And the dominant form of an FPGA is SRAM based, meaning that all of these control bits for the lookup tables and the routing is in SRAM. So you lose the state when you turn the power off. So the first thing most FPGAs do when you turn them on is they load in their configuration, the settings for these SRAM cells from somewhere. So often it's like a flash device on the same board. And sometimes it might get it over PCI Express from somewhere else. But until they get that, they can't do anything. And that means that there's a delay. It usually takes them about 100 milliseconds if it's a big FPGA to get this. And for 100 milliseconds, it doesn't know what to do. In most systems, it doesn't matter. It does matter in a few. So in some systems, an FPGA actually controls the power-up sequencing. And for those systems, it's not OK if the FPGA doesn't know what to do for 100 milliseconds. So there are some specialized FPGAs that will use flash memory instead of SRAM so that they come on instantly. Those ones are typically smaller, but because they come on instantly, they can do things like handle the power-up sequencing for a board. Most boards have like a lot of power for different chips, and if you actually bring them up in a random order, you'll fry the chips. So you need something that actually controls the sequencing of that, and that's usually an FPGA, but usually an FPGA that's not SRAM based. It's flash, so that it's awake right away. Okay, so I kind of went through a classic FPGA where you had logic and routing and IOs. Modern FPGAs have more than that. They have DSP blocks, which are basically digital signal processing, so multiply, accumulate, sometimes a bit more than multiply, accumulate now, sometimes special circuitry to help with FIR filtering and other things that you might do with multipliers. And they have embedded RAM blocks. So small, on the order of 20 kilobits or 100 kilobits, et cetera. So this is another architecture question. Blocks of SRAM. Okay, so I can build register files, and I can build program memory and buffering, et cetera, out of this. And all of those get connected to the programmable routing as well. And they're, again, typically built in columns because it makes it easier. All these DSP blocks will be the same width, and you can stack them in a column and connect them up to the programmable routing. It makes your layout easier to do. So these are die photos of a real chip. So it's from 40 nanometers. So it's not super old, but it's not cutting edge. But basically, these are like die photos that I had access to when I was at Altera. I can't go in now and get die photos of their like 10 and 7 nanometer FPGAs. So the reason I put these up here is just give you an idea of where does the area go. So the blue here is the logic. And the routing is integrated. So the routing is not actually separate from the logic blocks or the RAM blocks. It's basically the wires are running over top of it, and the switching is integrated into the block. So blue is the most common color here, and that's basically the logic with the integrated programmable routing. Red is also pretty common. That's the RAM blocks. This particular chip has 2 different sizes of RAM blocks. So some of these columns are a whole bunch of stacked 9 kilobit RAMs, and some of them are a whole bunch of stacked bigger RAMs, 144 kilobits. The DSP blocks are outlined in black here, so they're again in columns, and each DSP block's only like, that tall, so there's a whole bunch of them here. Each of them in this chip has 8 multipliers, so there's still a lot of multipliers here. But you can see there's less area devoted to the multipliers than to the RAM or the logic. In some recent devices, because they're focusing more on machine learning, the proportion of DSP blocks is higher, right? You might devote a higher fraction of your die size to it than that. Then the IOs are big, right? So IOs is a big part of your value proposition. So these are the general IOs. So general IOs means they're like somewhat lower speed, more programmable. These would be used to talk to memory, like DDR chips. And there are actually a lot of variations of DDR chips. Multiple generations. There's reduced latency DRAM. There are SRAM chips called QDR. There are other sensor chips that you might talk to, et cetera. So this can talk to all those. Whole bunch of programmability in them. There's a lot of clock management. So when you're talking to a bunch of other chips and you have a different IP blocks, like I told you, a typical design has sort of multiple kinds of streaming hardware. You don't get all that in one clock domain, so you have circuitry that is reasonably large to actually make you high-quality clocks. So all of these things outlined in black are, well, these things are phase-locked loops, which basically can multiply and divide clocks. So you can bring a low-frequency clock in off the board and multiply it up to make a whole bunch of faster output clocks. That's how you distribute high-speed clocks. You can't really send gigahertz clocks over a circuit board. You send like 50 megahertz, and you multiply up everything you want. And then there are also delay lock loops. Delay lock loops aren't as good at multiplying and dividing clocks, but they can shift them. And they can shift them quickly for clocks that start and stop. That turns out to be important in talking to DDR. Okay, so we'll talk a little bit about that later in some of the design examples. So a bunch of clock management. And then there are other IOs here on the edges that are like for PCI Express and Ethernet and SONET, basically high-speed serial interfaces. These are like your fastest IOs. They're intended to go long distances. Well, again, we'll talk a bit more about them later, but they're complicated. They embed the clock in with the data, and it turns out the speeds these run at, we couldn't make one set of IOs that was programmable enough and fast enough. We kind of had to split them. So the ones that are intended to be used for like serial, really high-speed interfaces, we had to dedicate certain IOs with a whole bunch of logic around them for those interfaces. So I guess the point of this is like there's a lot of area in IOs, so it is a big part of what you're paying for, even though people don't talk about it that much. So I like to talk more about processing. This is just the capacity in that 40 nanometer chip versus one of Altera's most recent chips, which is 10 nanometers. And I don't have that much to say about this except the numbers of everything go up, right? So logic went up by a factor of more than 3. The memory went up by a factor of maybe 5 or 6. The multipliers went up by a factor of 17. So that's kind of showing you that there's ever more importance in signal processing, both for like communications and machine learning. But the IOs don't change that much. Okay, so your processing counts, everything inside the chip is still scaling well with Moore's law. The general IOs actually, this is a somewhat smaller chip. It went down a bit. The number of high-speed IOs stayed about the same, but they got faster. They went from 8.5 gigabits per second to 58. So they keep ramping up the clock speeds of the IOs. And then there's a bunch, the clock generation is about comparable, and they're getting more system-level features, so embedded processors. You can build a processor in an FPGA just out of the logic, but if you think most systems will have a processor, you can make it more efficient by just pre-building a processor out of gates. And I showed you that most designs have processors in them nowadays, so this chip didn't have one pre-built. You had to build it out of the fabric. This has a quad-core ARM just integrated into it. So yeah, I guess my point in that is just core functionality continuing to scale well. IO's kind of always a problem. You can't really get more IOs. All you can do is try really hard to run them faster, which is challenging. Okay, and the last thing I was going to talk about is just how do we configure this. So I told you that when you wake up an SRAM-based FPGA, which is all the ones you would get from Altera or Xilinx, for example, it doesn't know what to do. So it has to load it in from something, like a flash chip or PCI Express, and before it knows how to do anything. It has some special circuitry to actually detect, like what's called the power on reset circuitry, to detect the power is coming up, because that special circuitry has to detect the power is coming up and clear all the SRAM. If that circuit doesn't work, basically you have all your switches are in a random state. You have shorts between power and ground everywhere, right, through all those programmable transistors. And that circuitry has to come on at a very low voltage. So it's actually one of the harder things to design in an FPGA because it's hard to model. It has to come up awake at a low voltage and shut everything else off. And there are some FPGA designs that I was part of where it didn't work. And if it doesn't work, the chip comes back and it won't power on. So this is like, again, you get an idea of the pain of making an ASIC, because when you're making an FPGA, it's like an ASIC. So you've spent millions of dollars, sent it out, it comes back, you try to power it on, it won't power on. The only thing you can conclude is the power on reset circuitry is not good. You have to try something and just go through the whole procedure again. So yeah, custom chips are a pain. So yeah.
I guess at least from what I've read, with the FPGA, you really only have one configuration bit stream that you're putting onto the FPGA. Something like a CGA doesn't support that sort of multi-complex bit streams or multi-complex configuration.
So we'll talk about that a bit later. So I mean, you can reprogram SRAM-based FPGAs as often as you want. So you can reprogram them over and over again, but it usually takes, I'll show you a diagram here very quickly. It usually takes 10 to 100 milliseconds, which is relatively slow. So there are some uses of that, but lots of cases where reprogramming it, that's too slow. So you should really just think of it as program it and use it until you power it off. I don't know if that answers your question or not.
If you have like two different configurations, let's say that you're switching between.
There are some devices that have done that. So there's a company called Tabula that made a time domain multiplexed FPGA. So they basically made 8-bit streams. So they had to have 8 times as much SRAM. So it would store 8 configurations and it would cycle through them. And the advantage, there's some advantages to that. You basically, essentially you can do different things. And you can use that to fit more circuitry in. Disadvantage is power. You have 100 million SRAM cells and you're cycling between them every single clock cycle at a high speed. That consumes a lot of power. So Tabula ran out of money. They raised $200 million and ultimately weren't successful. Doesn't prove that that idea is bad, but power was a big problem for them. So it can be done in FPGAs, can be done in CGRAs, but anything that does time domain multiplexing on the configuration RAM, you got to think about power. Okay, so the last thing I'll show you, but just quickly, how do you configure this thing? Let's see, let's mute the projector. Okay, so when it wakes up, the FPGA doesn't know what it is. The way that it basically is configured a lot like an SRAM. So there'll be some connection to the board. So this might be some IOs that are connected to flash memory. It might be some IOs that are connected to a PCI Express block that's on the chip. But it brings in data. Usually bring in quite a few bits at a time. Maybe it brings in 8 bits or 16 bits at a time. And it writes that at fairly high speed into a big shift register. Okay? And this shift, it could write them 8 bits at a time into a shift register that's 8 bits wide. Once it's filled up this whole shift register, basically all that 100 million SRAM cells that controls everything, it's distributed throughout the whole chip. There's no one spot where it is. It's in the lookup tables, it's in the routing. So basically, there are data lines coming out of this shift register that go all the way across the chip. Okay? So once I've loaded it all up, I basically, the FPGA control circuitry activates a word line. So it'll activate a line here that basically captures the data on all these into the SRAM cells underneath them. Okay? And then this will load for maybe another 5,000 clock cycles till it's all loaded up again. And then the FPGA will activate the word line that's next door to it. Okay? And another 5,000 SRAM cells will grab their configuration. So this is like shifting it in. And these are like word lines. So how long does this take to program? Well, maybe I've got 100 million bits, and I might be bringing them in 8 or 10 at a time. It takes me maybe 10 million clock cycles to program this. So that's not a big problem for most systems when you power it up, okay? Because that's still maybe 10 to 100 milliseconds, depending on how big the chip is. It is a problem in ones where you're controlling the power for other chips, but that's only a few systems. But it's a really long time compared to a microprocessor, right? A microprocessor can switch between instructions every cycle. And this is essentially the instruction for the FPGA, but it's like 100 million bits long, and it takes me maybe 100 milliseconds to switch to a new one. So it changes your FPGA programming model. Most users of FPGAs, you kind of treat it as I'm going to program you to do something, you'll keep doing it until I reprogram you. Yeah?
Just to clarify, this is when you literally just power on the FPGA. This is not when you configure the bit stream into it.
This is configuring the bit stream.
So it's the same kind of
yeah, like when you power up an FPGA, usually it'll load in either your bit stream or a default bit stream. And then you could also, without power cycling it, say, I want to program you again, but it basically does the same thing. We'll talk a little bit later about there are flows where you can say, I want to program this piece. Okay, so it is possible to do in FPGAs, but it's a bit more complicated. So this does change how most people use an FPGA like an easier to design ASIC, right? Like it's an ASIC where I can get a new ASIC very quickly, but I'm usually not changing while it's running what this configuration is, because 100 milliseconds is quite a while, and I don't quite know how to use that, unlike a microprocessor where the instruction's changing every cycle. So, okay, and the basic reason is a microprocessor is its instruction only encodes a few things. It's got maybe 1 or 2 function units. It's got a relatively small number of places where it's going to get the data from, like from a register file. This is encoding all of the switches that are connecting things together, and maybe 1 million lookup tables, so 1 million function units, and each of them has a unique code. So it's like a giant instruction word, and it does change how you use the device. Okay, so that was all I wanted to talk about today. Any questions? Okay, if there's any questions that you want to ask, just come up after, and otherwise I'll see you next week. I will post the reading soon for this week.